Hello. In this video, we're going to look at a couple of different ways that we can represent complex numbers. So if I start with the idea that a complex number is z equals a plus bi, now in this we are assuming that a and b are real numbers, then a is the real part of z and b is the imaginary part of z. We can represent this in Cartesian form using a sort of a Cartesian plane that's actually called the Argon plane, because instead of x and y axes, I have a real axis and I have an imaginary axis. So we'll represent this as a ordered pair A, B, where A is the real part of Z and B is the imaginary part of Z. So let's say I have a point somewhere over here, which is the point, the ordered pair A, B. I'm representing this in the first quadrant. There's absolutely nothing to prevent it from being in any of these quadrants or in fact on an axis. If it's on the real axis, because b is 0, then it's a real number. So real numbers do work on this plane as well. They're just represented on the number line, the real number line. And a pure imaginary number would be on the imaginary axis if a is equal to 0. But assuming that this is a point that represents a particular number, every number is going to be represented by a unique point in this plane. Because of that, we can define the position of that point instead of using the horizontal and vertical displacement, or the real and imaginary parts of that number. We can represent that position by an angle of rotation, now angle in standard position, so taken from the positive real axis, and a distance, which would be represented by the modulus of z from the origin. And I think it doesn't take much convincing to realize that that distance has to be the modulus of z, because this horizontal distance is a, the vertical distance is b, absolute values technically of those distances if I'm talking distances. And so z, the modulus of z, is the square root of a squared plus b squared, just the Pythagorean theorem here. So that distance, and then whatever angle of rotation happens to appear here. What we can also note is that the sine of theta would be b over the modulus of z, which means that b is actually equivalent to the modulus times the sine of the angle. And likewise, the cosine of theta is equal to a over the modulus of z. And this, again, this works for no matter what quadrant I'm in. Sometimes I'll get a positive a value or a negative a value, but that's still going to be the cosine of the angle. This means that a is the modulus times the cosine of the angle. What that means for us is that instead of representing this using values a and b, I can actually represent z using the modulus of z times the cosine of the angle plus the modulus of z times the sine of the angle I. And what we often do is we represent this as the modulus of z, and then we just write cis theta, where cis is understood, so the CIS is understood to be cosine of theta plus I times the sine of theta. This is a bit of a shorthand, and sometimes in lieu of using the modulus of z notation, we write r cis theta, where r is the modulus of z, but we use r because it is also the radius of the circle that would be traced if we went through all of the possible angles, theta, for that radius, for that modulus. So this is a notation that we sometimes use where we are representing the modulus and the angle of rotation. The angle of rotation is also called the argument of this complex number. So the modulus argument form is what we have here of the complex number. We're representing it using cis, where cis is understood to be cos theta plus I sine theta. All right, this form, the modulus argument form, z equals r cos theta plus r I sine theta, or what I've just said, this is z equals r cis theta, is a shorthand. Can also be written in polar form as z equals r times e to the power of theta I, where r and theta mean the same thing they just meant. So theta is the angle of rotation, the argument of this number, and r is the modulus of this number. To prove why these are equal requires Maclaurin series, which is something we'll come to later in this course. So we will actually prove this relationship, this form, later, but for now we're going to continue to use it. So let's convert a value that's given in Cartesian form into polar form. This is going to start by going through the modulus argument form. So I need to figure out what are the modulus and argument of this complex number. So what we're saying is that root 3 has to be equal to r cos theta, and -1 has to be equal to r sine theta. Oops, equals, there we go. And because, of course, we would have to divide by r, that's going to be root 3 over r equals cos theta, and -1 over r equals sine theta. Now, that's going to likely give us some, there might be some familiarity to these. For example, if you just happen to notice, well, root 3 over 2 and -1 over 2, those are very common sine and cosine values that we see. It's not always as immediately obvious as that, so we'll go through a process where essentially I think about this as, if I think about what that would be in Cartesian form, so root 3 -I, that's going to be down here in the fourth quadrant, where the way that's written, the horizontal distance is root 3, the vertical distance, or the vertical value, is -1, the vertical distance is 1. I can obviously use the Pythagorean theorem to find what r has to be. So r is the square root of 3 squared, which is 3, plus -1 squared, which is 1. So r is equal to 2. So we do get to what I had said, that root 3 over 2 equals cos theta, and -1 over 2 equals sine theta. You wouldn't necessarily have to do that work if you do happen to recognize these very common sine and cosine ratios. So because these are known ones, we have a special triangle essentially here. We can conclude, now theta is the angle of rotation. So theta is the angle all the way around the outside and not the acute angle inside of that triangle. The acute angle, or the reference angle inside of that triangle, is pi over 6, but this is actually going to be 2 pi minus pi over 6, so 11 pi over 6. So we have theta equals 11 pi over 6. So in order to figure out the modulus, you can use the Pythagorean theorem. In order to figure out the argument, you have to think of angles in standard position and which quadrant are you going to be in, and so on. So the modulus here is 2, and the argument is 11 pi over 6. So if I were writing this in modulus argument form, this would be z equals 2 cis 11 pi over 6. But in polar form, this is z equals 2 e to the power of 11 pi over 6 I. And there we have it.